Greetings to doctor. My name is Pravindra, son of Kannan, and my matrix number ID is CE210 and 202. So today I want to explain from lab number 8, activity number 1, that is my part. So for activity number 1, we have to create circuit like this, and insert the values according to the given, and I have to simulate and have to state the simulation value for the AC voltmeter and AC ammeter. For the load R and L, then the loads are here. For this part, we have to create the circuit like this first, and check the values are the same. 14.14 volt, 50 hertz, AC ammeter, AC voltmeter, and R and L are load. For R load is 210 ohm and L load is 0.4 Henry. So just run the simulation. For the first load, the AC ammeter shows 40.9 milliampere and the AC volt 9.99 volt. So we just change the inductance value from 0.4 to 0.8. So we run the simulation again. So for this one, we got AC ammeter shows 30.5 milliampere and the AC volt is same, 9.99 volt. And we pause and change the inductance value from 0.8 to 1.0 Henry. So we run the simulation. So for this load, the AC ammeter shows 26.4 milliampere and the AC voltage is still same, 9.99 volt. So after this, the inductance value will be 0.4 and only the resistance value will be changed. So resistance value is 390 ohm. So run the simulation. So for this load, the AC ammeter shows 25.4 milliampere and the AC voltage is still same. So for load number 5, we put 470 ohm. So we just run the simulation. So the AC milliampere shows 20.6 milliampere and the AC voltage is 9.99 volt. The AC voltage are still same. As for the final value, we put 860 ohm for the R1. So run the simulation. So for the last load, we got 11.5 milliampere and 9.99 voltage. So from this activity, we can know that the AC voltage are still the same even the loads are changed, but the AC ammeter is slightly decreasing due to the load changes. That's all from me. Thank you.
Greetings to doctor. My name is Nur Natasha Amira binti Manasir and my metric number is AA 2041. Now I will explain the activity 2, which is a parallel resistive inductive load circuit. The circuit is RL parallel, and we need to find the current and the voltage here, and the voltage is 10 volt AC and the frequency is 50 Hz. So this is the circuit that I have connect all together. The value of amplitude is 10 volt times with RMS set 2. We got 14.14 and the frequency is 50 Hz. For the circuit, we need to add one resistor here because if we not add the resistor, it will show fatal simulation error. So in order to get the simulation, we add this resistor with 1 ohm value with just the small value of resistor. And then for the first value is 200 ohm parallel with 0.4 inductor. So 210 and 0.4, we run the simulation. Okay, after we run the simulation, we got the AC ammeter is 92.1 milliampere and the voltage is 9.94 volt. After that, we stop the simulation and we change the value to 0.8 inductor. And we run the simulation. We got 60 61.9 milliampere and the voltage is 9.94 volt. After that, we change the value of inductor with 1.0H and we run the simulation. We will get the AC ammeter with the current value of 57.2 ampere and the voltage is 9.94 volt. After that, we need to change the value of the resistor with 390 and then the inductor is 0.4. And then we run the simulation. We will got the AC ammeter with the current value of 82.8 milliampere and the voltage is 9.96 volt. And then we need to change the value of the resistor with 470 ohm. After we run the simulation, we will got the current value is 81.5 milliampere and the voltage is 9.97 volt. And lastly, we need to change the value of the resistor with 860 ohm and we start simulation and change it to 860 ohm and we run the simulation. We will got the current value is 79.5 milliampere and the voltage is 9.98 volt. After that, we need to compare the simulation value with the manual calculation. So this is the manual calculation that I've done, but to make it easier, I will make a comparison from this table. Okay, so this is the calculation value and the simulation value for the voltage and current. Okay, as we can see, the current value from the manual calculation and the simulation value has a slightly difference, but they don't have so much difference. It is almost nearest together. It is because we need to add one resistor with value of 1 ohm, because if we didn't add one resistor, it will display error and the value of ammeter and voltmeter can't be shown. So it's because use of small resistor to put some impedance in the loop, which is probably realistic anyway without changing the operation of the circuit too much, and the value also didn't change too much. So the difference also can be because of rounding off the value from the manual calculation and adding a resistor in the simulation software makes it a little bit different, but the difference only in a small value only and almost near with each other. Overall, the value in manual calculation and software are proof that it fulfills the theory. As we can see, the voltage is 10 volt and the simulation is 9.9 something, which is near to 10, and the current also near together, the value with the calculation and simulation.
Hello everyone, my name is Shivaran Anaki Murugan. My matrix card number is AE190089. Today I am going to explain you all about the activity tree, which is a series resistive capacitive low circuit. So the given voltage, AC voltage is 10 volt and 50 Hz of frequency. Now we are going to use an AC supply, which is a V sign, and we're going to use an resistor and a capacitor. So to measure the ammeter, we are going to use an AC ammeter, and to measure the voltage, we are going to use an AC voltmeter. Now we are going to complete the connections. The negative terminal of the capacitor is connected to the negative terminal of the AC supply, and we connect the voltage to measure the voltage across the resistor and the capacitor, and we set the ammeter to milliamperes, and we set the frequency to 50 Hz and the VRMS to 14.14 volt. Since the given for the first case, we are going to use resistor value of 390 ohm and the capacitor of 2 mu f, and now we run the program. The voltage recorded is 9.99 volt and the given current is 6.16 milliampere. For the next case, we are going to use the same resistor but change the capacitance value to 4 and run the program. We will get the same voltage, which is 9.99 volt and 11.3 milliampere of current. For the next case, we are going to use 8 mu of capacitance value and run the program with the same resistance, and we will get the value again. The voltage is same but the current increases to 17.9 milliampere. So for the next cases, we are going to change the resistor value of 210 and the capacitance of 4 mu f and run the program, and the voltage is still the same and the current slightly reduced to 12.3 milliampere. For the next case, we stick to the same capacitance and change the resistance value to 490 ohms and run the program. We will get a value of 10.7 milliampere. As you see, if we keep increasing the resistor, the current decreases. So for the last case, we use a resistor value of 860 ohm and we'll get a current value of 8.51 milliampere, whereby the capacitance value is remain the same, which is 4 mu f. So for the next case, we record the values in the table below. And using the given formula, we calculate the impedance and the calculated current value and the total impedance for each cases, and we record in the table above, which is for the first case we have a 168.5494 impedance. The current calculated was 6.1026 and which correlates with the simulation value of 6.16 milliampere. So as we see from the table above, as the resistance value is remain constant and the capacitance value increases, the current also increases, whereby when the capacitance is remain the same and the resistance is increases, the current decreases. That's all from me. Thank you. For activity 4, it is quite similar with activity 3, but the circuit is connected in parallel. The resistor is connected parallel to the capacitance, where the voltage value is stick to 14.14 RMS and the frequency is set to 50 Hz. So for the first case, we are going to calculate for the current and voltage for 390 ohm and 2 mu capacitance. The current recorded was 26.3 milliampere and the voltage is 9.99 volts. For the next case, we are going to calculate for the 4 mu f. With the resistance stick to 390 ohm, we will get a current value of 28.5 milliampere and the voltage is still the same, which is 9.99 volts. For the next case, we stick the resistor to 390 ohms and change the capacitance to 8 mu farad. And now we will get a value of 35.9 milliampere and 9.99 volts. Now we are going to stick to the same capacitance values, which is 4 mu f, and we are going to change the resistor to 210 ohms. As you see, once we change, we have a highest current recording, which is 49.1 milliampere, and the voltage is still the same, 9.99 volts. And we are going to increase the resistance to 490 ohms, and we will be getting a value of current values decreases to 23.9 milliampere and the voltage still the same. Last but not least, we are going to use a resistor of 860 ohms and we will be getting a output current of 17.1 milliampere. And we repeat the similar step, record the values in the table for the current values and the voltage values, which is the simulation part, and using the given formulas we will do the manual calculation to calculate the impedance, total impedance and the current output for each cases. So we will get the current which is correlates to the simulation value once the calculation is done. As you see, for the parallel case, if the capacitance increases, the current also increases. However, when the lowest resistance and the 4 mu f capacitance is used, highest current value is recorded, which is 49.10, and if the capacitance is constant and the resistance increases, the current decreases. That's all from me. Thank you.
So I'll be explaining about activity 5 again. So this is a 50 VAC connected with 50 Hz frequency, connected with RLC is load in series. We need to measure the ammeter and the voltage. So these are the values that we are required to simulate. So this is the circuit in Proteus, and the AC input source has been set to 70.71. This is because 50 times square root 2 is 70.71, and the frequency is at 50 Hz. We are using a sine wave, sine voltage source. There's the AC ammeter connected, has been set to milliampere. A resistor in a generic inductor, a generic resistor, and a generic capacitor. And AC voltmeter has been set across parallel to the load to measure the voltage. So now let's simulate. The first one is we need to set the resistor as 390, the inductor at 0.4 Henry, and the capacitor is 2 microfarad. So as we run the simulation, we are able to see that it's 33.3 milliampere, and the voltage across the load is 50.0 volt. And now let's increase the resistors value to 470 and keep the rest the same. And now as you can see here, it's 32.8 milliampere. The voltage is still the same at 50. Now let's increase the resistance even more to 860. So you can see the resistance here is 29.6 milliampere. So now let's bring back the value of resistor back to 390. And now let's increase 0.6 Henry from 0.4. So 0.6, the rest all is kept the same to the initial. We get 34.8 milliampere at 50 volts. Now let's increase even the value to 1.0. So from here you can see it's 38.0 milliampere at 50 volts. Now let's bring this back to 0.4 and increase this to 4 microfarad. You can see the value is 64.9 milliampere at 50 volts. And finally, let's increase this to 8. And the AC emitter reading is 105 milliampere at 50 volts. So that's all from me for this circuit. The manual calculation for activity 1 and activity 5 are similar to the simulation. So that's all from me. Thank you.
Hello to Doctor. My name is Natasha Amira binti Manasir and my metric number is AE 2041. Now I'll be explained again for the activity 6, the parallel RLC load circuit. The circuit is almost similar with the activity 2, but the difference is we need to add one capacitor here and we need to measure the current and the voltage here. So the value of voltage is 50 volt and the frequency is 50 Hz. This value is resistor 390 ohm, inductor 0.4 H and capacitor 2 microfarad. So this is the value and we run the simulation. After we run the simulation, we got the current is 384 milliampere and the voltage is 49.8. Okay, as usual, we need to add 1 ohm resistor here in order to avoid the error. So just a small value of resistor not affect much the value. After that, the second value is 470 ohm, 0.4 H and 2 microfarad. So we run the simulation and after we run the simulation, we got the current is 377 milliampere and the voltage is 49.8 volt. After that, the third value is we just need to change the value of resistor, which is 860 ohm, and we run the simulation. After we run the simulation, we got the value of current is 366 milliampere and the voltage is 49.9 volt. And then the fourth value, we need to change the value of resistor is 390 ohm and the inductor 0.6 H. Okay, and then we run the simulation. We got the current is 264 milliampere and the voltage is 49.8 volt. Change the value of the inductor is 1.0 H. And after we run simulation, we got the current value in the AC meter with value 180 milliampere and the voltage is 49.8 volt. And for the sixth value, we need to change the value of the inductor with 0.4 H and the capacitor 4 microfarad. And then after we run the simulation, we got the value of the current is 35.4 milliampere and the volt 49.8 volt. And then for the last value is we need to change the value of capacitor with 8 microfarad. And then after we run the simulation, we got the current value is 296 milliampere and the voltage is 49.8 volt.